Kim Henriksson, and I work for Sensact as a proof of concept wizard.
And then we also have with us Tobias Edman.
Hi, good morning, everyone.
Tobias
for the Swedish
Edman.
National Space Agency.
Exactly. And we will hear a bit more from Tobias in just a short while. But before that, if you are not from an AI Sweden partner organization, you may not know AI Sweden very well. And we are a organization with the mission to increase the use of applied AI in Sweden for the benefit of society, for Sweden's competitiveness, and for the good of everyone living in Sweden. And we do this together with the partner organizations that we have. And we now have over 100 partners with a mix of public sector, private sector, so everything from startups to corporates, academia, authorities, municipalities, regions, etc. And Kim, the space proof of concept, why are we doing this event?
Yeah, this event is all about exploration and creativity. We, AI Sweden, together with the National Space Agency and the partners, recognize that there are lots of opportunities in space, and we can help, both with facilities and funding and partnering up with others. So therefore, we invite you to now be inspired and explore what can be done in space and how it can be done, particularly from an artificial intelligence perspective.
That's right. And you might have heard just when we started the webinar that this webinar is being recorded. If you have any questions throughout this open session that will go until 10:40 something, please use the Q&A tab or the chat function that you see at the bottom of your screen. And we will, for example, with the session where Fuglesang is doing a presentation, leave 10 minutes for questions for the audience. But if you have questions for the other speakers, please type them in, and hopefully they will be able to respond by replying by writing. Otherwise, we'll try to see if we can gather questions and then respond to them later. But so this is the open part of this webinar that will go on to about 10:40. After that, we'll go into a closed session that we call the brainstorming session that is part of the collaborathon. And to the collaborathon, we have invited people to apply to be part of actually getting access to the Edgelab, where the Space Data Lab and Rymdstyrelsen Space Agency have provided data from the Copernicus satellites. And then the collaborathon will start from after lunch and go on all the way till Thursday. And then we'll wrap this up with an event where we show the proof of concepts that have come up from this event between 3 and 5 on Thursday. So please join us for that open session again if you wanted to see what came out of this collaborathon. So with that, we leave the word to Tobias to let us know your thoughts on why it's important to do these kind of events and the Space Agency's thoughts.
Yes, absolutely. You must stop sharing your screen, I think, if I should.
Yep, we'll do that right away. Thank you.
Okay, no problem. I see if I can try to do this again, and it seems to work. Yes. So, hi, welcome everyone. My name is, as said, Tobias Edman. I'm head of innovation and public benefit at the Swedish National Space Agency, and we are the Swedish government body for space innovation, and funding of space research and development. And we believe that this, and I'm also here as part of the Swedish Space Data Lab, which we have initiated from the Space Agency and are part of. And we see actually that, I mean, space, it's really all about data. So space, why are we doing it? Mostly space is actually most about data. It's of course a whole lot of hardware that needs to be developed, manufactured. It's really cool putting things out there, but what are they actually doing? They are collecting data or transferring data in different ways. As long as you're working with a civilian space programs. So that's our main target. And we also have the global development goals. We see them as really, really important, and we see that space has something to fulfill there, collecting all this data, making all the data available, and connecting people in a good way. And then, of course, where it's a lot of data, there's a place for AI. And we try to work to promote AI with space data during the whole system. And we have been working mostly on ground, but we think it's really important to take this up into space as well. So having the capabilities of doing algorithms in the actual spacecrafts is really important. And this is more or less a simplified way of how we're working in the Swedish Space Data Lab. So from the government perspective, we are mostly at the moment interested in the Copernicus data, as they are free available, and we have made huge investments in them. And that would be the satellites up here. And then we're working, And then we're working with an open data cube at the Space Data Lab to collect all the data, sort it, index it, make it available in a good way so that you have analysis-ready data. And then, of course, making it possible to combine it with climate data, geodata, socioeconomic data, almost any other data, because the space data won't actually stand by itself. You need to combine it, you need to aggregate it, you need to churn it and chunk it and process it in good ways. And when you've done all that, then it's time to get into the actual algorithms and the processes, and to make information and decision support, and to present it in good ways. And from my perspective, working with data exploitation and public benefit, that's actually the main target for this, for working with space, is to get good information and good data. And this is what we do down in the ground segment, working on ground. But of course, there's an opportunity to work with data also up in space. And this is just very simplified. It's more than 2,000 spacecrafts up there now. There are plans to make them hundreds of thousands. And I think that's when the actual AI part comes in a good way. If you have hundreds of thousands of spacecrafts swirling around the globe, then you need to have really good space situational awareness control. You need to have the navigation of the spacecrafts, the maneuvering of them. You need to have a lot of the functionality up in space as well. And that's because you have lag times. They're quite far away. You have many of them you can just communicate with them when they are over the ground stations, etc., etc. Then for Earth observation, which is what we have prepared some data for today, then there you also have the timeliness, you have the accuracy, you have the risk of disturbance, etc., when you're transferring the data, and also the bandwidth. You can't download, it's a limit in how much data you can download. So the more you can process on the spacecraft, the better actually for those aspects. So that's what we are involved in with AI Sweden and with the Space Data Lab, is to promote AI and data, and to really make good use of the data that comes from the different space systems. And that might be a bit less than 7 minutes, I think, but I give the words over to Ebba now.
Thank you so much, Tobias. And here you have Tobias' contact details, and we will also share our contact details in the chat very soon. And we have quite a full program in this webinar session. So we'll move right ahead with our next speaker, Fredrik Bruhn from Unibap. And Tobias, if you want to stop sharing, and then Fredrik can probably start sharing.
Yes, thanks.
There we go.
There, we'll see if we have, there's Fredrik. Good morning, Fredrik. We know that you are in between other sessions that you're doing, or other presentations. So we're really happy to have you.
Well, good morning, everyone. And it's great to be part of this session. And thank you for inviting me. I think this is a very timely topic, as you already said, and Tobias expanded on, that onboard intelligent data processing will be an important part of the future. And the reason being multiple different reasons, but one of the big reasons is that we are today downloading terabytes of data every day. And the last number I saw was in the order of maybe 5 to 7% utilization of that data. So most of the data being downloaded today is being thrown away or just stored on a hard drive somewhere. And one way to increase the utilization of data is to go for those low latency data products that we will discuss in my talk here. And for me, a very low latency data products means that it's less than 1 minute from capture, analytics, and down to the user. So you're cutting the time from weeks, maybe months even, down to minutes, and that's very significant. So I'm also very happy to say that one of my colleagues, Josephine Nittler, is with you at the Edgelab today. So you can always talk to her today, tomorrow, and I believe also on Wednesday. And as you already said, I will have to jump out after this presentation, but obviously I'm available for questions and things like that afterwards. So let me give you a 14-minute presentation regarding Space Cloud and really the Space Edge, because what we are doing together with the European Space Agency, the Swedish National Space Agency, and a lot of partners is to build up an ecosystem where you can deploy applications in space, just the same way you do on an Earth terrestrial-based cloud system. And that's really the key, to do this in the same way that you do on ground, so that you can reuse all of the software and you can harness that magnificent educational base we have.
Okay, let's see. It seems like we might have lost Fredrik there for a second. So we'll just see if we can reconnect to the meeting and continue. He has 1 minute extra for his presentation. So we hope we can fix this technical issue. Otherwise, we might have to go ahead with the next presentation. But we really want Fredrik to share his thoughts. So let's just give it.
That's why you never should do the introduction. You should go straight to the most important part at once.
Exactly. But meanwhile, Tobias, you had a question in the chat or in the Q&A tab. Maybe you can type an answer or even actually start answering it live.
Well, what kind of AI solutions are you looking for and the purpose? I would say that we are looking for any kind of AI solutions. We are not really picky about that, but we think the purpose would be to have better Earth observation and analytics. Most of the really good things that has been done doing Earth observation really needs that you have someone looking at them afterwards, saying, okay, this is good, this is not good, this is good, this is not good. That you have a really, I mean, even if you really automate it, you're using a lot of ML techniques and AI, you need to have this human eye to see, okay, is this good or is it not good? And then you can continue what is good. So that would be, I mean, something amazing, really working more with that solutions that where you don't really need so much of a human eye on it, that you can really train the AI to do what the human interpreter does. And I mean, we're not there yet, so that would be amazing. And then it's, of course, I mean, up in space, it's a lot about these latency issues. It's about the autonomy of the spacecraft being able to do different kind of maneuvers and to do that in a timely way to avoid space debris and so on. And I know that also when we stop the linearity of the communication satellites, where the satellite need to be able to communicate with a lot of different responders, to have when you not send TV, but you use it for internet broadcasting, for example, then you need to optimize also that part.
And going into the purposes, I mean, some purposes are obvious. You want to make it more efficient to use AI, but are there any other purposes that you see, like why you want to really go to AI and use that in space?
I think that, I mean, to some extent it would be, I mean, it's always about efficiency and making things in the best way. And then, of course, if you look at the global sustainability goals, then we have a lot of, I mean, we have a lot of issues to work with. We have, we need to work with water quality, with food production, etc. And now I see Bruhn, so I think Fredrik, you can take it over from here.
Yeah. You lost 1 minute there, Fredrik, but I think you might have still about 13 or so.
So let's try this again. So I'm in a studio in Västerås and the network went down.
Okay, yeah, we're really happy to have you back again. So,
let's
I think
hope
we lost you on the second slide or something.
All right, so let's recapture and see if you can see this. Is it working?
Yes, yes.
Okay.
It works, looks good.
Okay, so very briefly, Unibap is an AI data-driven company working in space and smart industry. We were founded in 2013, and we have a trademark called Space Cloud, and that's interesting because it wasn't really trademarked anywhere in the world. Space and cloud are trademarked, but not Space Cloud as a combination. We work with a lot of international customers. We have had our base in North America for quite many years, working with NASA, Boeing, and Lockheed Martin and other companies. And we recently came back to Sweden and Europe working with ESA. So even though we've been a Swedish company, we've done a lot of work in the US. But first of all, what's interesting, and I think this is something that the community can take with them, is that we are doing a lot of spin-ins from industrial applications. So I just told you that we have smart industry and we have space. When it comes to smart industry, I will show you only one example of what we do and how we can take that into space. And we are working with some very large companies like Volvo and Sandvik and Husqvarna, for instance, on the industrial side. And what we do is real-time decision-making in production lines. So it's high reliability, it's very cost efficient, and it's also increasing the production rates. And this is an example from Umeå. Sweet Tree is the technology company of the forest industry in Sweden. So they are going to manufacture clones of spruce in this case. And only in Sweden, they are planting, give or take, 200 million spruces a year. And if you do clones or somatic embryos, what they are called scientifically, you can actually tailor what the trees look like, and you can select a suitable tree for a suitable growth zone. And the idea here is to have a fully autonomous manufacturing site up in Umeå, where you have in a sterile, clean environment, much similar to the satellite environment in space, you have an autonomous operation where our skills based on AI are doing picking, inspection, planting. We are doing robotic motions based on AI decision-making in real time. And the pilot plant will do about 3 million of these clones per year. And when it's fully built out, we will do about 200 million plants per year, which corresponds to about 1 million decisions, or 1 billion decisions, I would actually say. So this is an example of what we are able to do in industry today. And the software base here can be reused for space. And that's really what we are going to talk about now. So I'm going to show you a few examples how cloud edge and storage can be done in space. And as I said, we are doing this development together with the European Agency, Space Agency, together with SNSA. So let's have a look. What is Space Cloud and how does it work? I tried to summarize it on one slide for you here. And Tobias already covered a lot of this. So we're looking at very low latency data products. So you're sorting, indexing, and meta tagging the data directly in space. And then you optimize the downlink so that you really download the data that has a customer value. And what's also interesting is that we talked about decision making, and Tobias also talked about space situational awareness. When you have tens of thousands of satellites out there, you're going to need distributed autonomy. And the way to get distributed autonomy is to have decision making on the satellites and then interchanging those decisions so that you have a multi-agent network that can reason. And this is being enabled by onboard cloud computing. What is also interesting is that you can start to optimize the communication links as well, because if you have prioritized all the data in the spacecraft, you can send that priority list down to ground, and then you can do your tasking of ground station based on those priorities as well. So there is a tremendous amount of effects here that can be leveraged if this is done properly. And the way you want to do it is to make it as close to the Earth or terrestrial based equivalent as possible. And the way we do that is in the following. So we have basically 4 boxes where you obviously have development kits and you have space flight solutions. So you need to have hardware in space to be able to run this. So these are the classical upstream parts.
It seems that we might have lost Fredrik Bruhn once again, which is quite unfortunate because...
And he was just getting to the point.
Yes, this
of
part
the really cool stuff
is really, really exciting. And just a teaser from me for that's going to hold the next presentation here is that we actually aim to have a few of these development kits available in Edgelab, and also with the help of Unibap and the Space Cloud have a connection to the actual equipment in space.
And there we have Fredrik again.
Yes, and I think we covered for him quite well. So please go ahead, Fredrik. You're still on mute though.
I'm terribly sorry for the network coming and going, so I'll try to be quick so we can fit it within the network allowable time.
Thank you.
What's important here really is that the framework is something that we have developed with ESA. It's open source. You can download it from our website, and it's very similar to Android SDK. So you have a proto buffer layer that defines the API. And if you stick to that API, we can immediately orchestrate your application in space. And then obviously the big important thing here, as Tobias said going forward, are the applications that enable the reasoning on board. And I'll show you a few quick examples of applications that are actually in space already. First of all, very quickly, if you or the viewers have any experience in cloud development, you would be familiar with a chart like these. So you have the operating system with bells and whistles at the bottom. You have the framework, which the APIs exposes to the applications, and then you do some form of cloud integration. And what might be of interest for the audience is that we announced in December last year a big partnership with a small American company called Amazon Web Services, where we stated that we are integrating AWS cloud storage and edge services into Space Cloud. So you can have a seamless integration with AWS all the way into the spacecraft. 2 missions that are using this, the NASA HiTi mission. It's a small 6U CubeSat with a hyperspectral cooled detector on board. So it's deep thermal infrared. They are doing 4 different applications: volcanic activity detection, forest fires, precision agriculture, and oil spill detection. This one is being launched at the end of this year. It's being integrated now. We have delivered flight hardware to the US. The ION SCV was launched in June this year, so it's already in space. And the video here shows the ION being released from SpaceX. The ION is here. What's interesting with this guy is that it carries in space a flooding application by Trillium and the Frontier Development Lab in partnership with ESA. And you have a mid-air aircraft detection app as well. We are flying hyperspectral image compression by the Swedish software company called Enea. You have fault detection, isolation, and recovery, which is called FDIR in space language. by ESA. We have vehicle detection ourselves. We have a ship detection application from Irish Robotic on board, and there are in total 22 different applications on this spacecraft. I did want to show you this example. So this is a application for Space Cloud developed by the American company called Cheran. And the way it works is that they took an existing application and they ported it to Space Cloud. And it was ported together with a software suite called NVIDL. So if any one of you have a background in geospatial processing, you would probably know that NV is a big software suite by L3Harris that have modules for SAR and LiDAR and hyperspectral data, et cetera, et cetera. So we incorporated the entire NV suite into the spacecraft, into Space Cloud. And then we ran this application on top of that. And the purpose of this application is to demonstrate extremely low latency data products. In this case, we analyze 100 square kilometers, 8-band multispectral imagery, and we identify all moving aircraft, and those are aircrafts moving above Earth. And we can detect that down to about 1 pixel in size. And what's interesting here that I would like for you to take with you is that this entire process of porting NV, porting the existing application for onboard machine learning took about 40 hours of work to do. And this one is flying in space on the ION SCV-3 spacecraft. And what kind of data products can it generate? So within 1 minute, we can, in 100 square kilometers, pick out every single aircraft that is visible. We can send down the geolocated coordinates, and we can also send down a KMC file. That is the file that is highlighted here, which you can overlay on Google Earth, for instance. This happened to be an aircraft over Saudi Arabia, but it works over sea as well. And if you take into account that it took about 40 hours to port this existing application into Space Cloud, you really realize that this is a game changer, because you can now start to orchestrate quite advanced applications in space quite easily. I wanted to highlight this also. We started a talk by talking about distributed spacecraft autonomy, and NASA is standing up a big simulator at the NASA Ames facility in Silicon Valley. They will have roughly 100 different nodes simulating different architectures, and 25 of those nodes are based on Space Cloud. So we are actually, from Sweden, providing the backbone for this new NASA research facility. And this hardware has already been developed, and it's already been shipped, and it's being integrated at NASA as we speak. And we are very welcome from Sweden to participate in the NASA research regarding DSA. So that could be of interest to bring into this slide, the space edge, the next frontier. So I'm happy today to announce that Unibap is joining AI Sweden, and we are making this infrastructure available to AI Sweden as well. And the way I see it, you saw the DSA simulation cluster from NASA. That could be one avenue, that if we have autonomy applications in Sweden, we could test that at the NASA DSA facility. But we can also do experiments in space. So the way it could work, if we wanted to, is that the Space Data Lab that Tobias talked about can be an infrastructure to provide data to train machine learning applications based on historical data. So for instance, if you look at that World Floods app that is flying, it has been trained of flooding data, historical flooding data. And then that machine learning model is being inferenced in Space Cloud in space. And what we can do together with the Edgelab, that some of you might actually be physically at today, we can do testing on representative hardware. So Kim will tell you more about this, but they have a wide setup of different hardwares that can be used to demonstrate this. And then you can automatically, the good applications that you would like to test in space, you can push into what we call the Space Cloud Registry. That's a Docker registry, because we use Docker to orchestrate the applications in space. And we can push that out onto real flight hardware located in Uppsala, where you can test your applications on real flight hardware. And if it passes the flight hardware test, you could actually upload this into a space edge, a space cloud compatible satellite, and then we orchestrate your applications in space. So it really would represent an end-to-end seamless cloud experience in space, just the same way you would do on ground. And we would reuse all of the tools that you are familiar with. For instance, in the previous picture you saw
And there we lost Fredrik again. We'll see if we can get him back. Otherwise, I think he did a really nice segue into your presentation, Kim, about the Edgelab. And I believe that Fredrik might have to, oh, there we go, Fredrik. Are you back with us?
I'm back.
Do you want to finish up?
I'm back and I'm done here. I'm just gonna say thank you very much. And if you have any questions, talk to Josefson physically there, or send us questions and we'll be happy to answer more questions. If you do have some minutes, I can perhaps answer some questions now as well.
If you have some minutes to stay on, Fredrik, please
Sure.
Type your questions into the Q&A function and Fredrik can respond to them. So thank you so much for the presentation. Really nice to hear that you are joining AI Sweden. We're super happy about that. And we'll move to Kim's presentation to hear more about the Edgelab.
Yes, I'm just gonna share it. So here we are, and as Fredrik already alluded to, we are aiming to be able to facilitate experimentation here. So looking into what the fundamental challenge is here is that we want to create value, and we have the ability to generate a large amount of data. But there are some difficulties in actually using this data. It's, from a privacy perspective, definitely a challenge, and that's something I think we all want to preserve. It's the cost of an ability to transfer, especially from space. When it comes to large amount of data, the bandwidth is limited. There are latency issues and also compliance and security issues. For instance, transferring data between countries, between organizations. A good example is healthcare, between hospitals. And therefore, we can see that the direction we have right now is not really sustainable. And I'm from the automotive industry, so I'm going to have some example based on automotive industry. But I want to highlight that on a fundamental level, the core problems and challenges are roughly the same. And that's why we are excited to be a part of this event and also the lab. We were thinking a bit about what is the based on the challenge here, what is the actual fundamental question? If the data is born on the edge, can't it stay on the edge, on the satellites, in the vehicles, in the hospitals, in the manufacturing equipment? So isn't it true that what we really want to do is aggregate knowledge? And that's where we come to federated learning, the next iteration or next step of machine learning. And I want to take my time here actually, because some of you might be familiar with federated machine learning and some of you might not be. So we look into machine learning as a concept in itself, is where you train a model, there you traditionally or typically collect vast amount of data to one location, and that's where you train it. Federated learning tips this on its head, and the training actually occurs where the data is. So an example here is on our left, where we start basically in a cloud or a core app at our core with a seed model, share that with a large set of clients, edge nodes, many names for these, and the model is trained locally on the local data available to that specific node. The model parameters from each node is then sent up, aggregated into what one can call a supermodel that becomes better and better all the time, and this can be iterated. So in theory and partly in practice, we can now train models without actually sending over the data. Swarm learning, as HPE will talk more about later, is another niche of this where you have no central point. If you look into where this might be applicable, we quite quickly see that it's basically everywhere. Healthcare, real estate, space, for instance, retail, logistics, manufacturing, any IoT. So it's very much a field that is evolving quickly. And with evolving quickly, we realize that on a description level, it's quite easy to understand the concept, but actually, how do we do it? What framework should we use? What equipment should we use? How do we actually train this model? How do we verify that it's good? And we realized we don't have that knowledge, and we want to gain that as quickly as possible. That's why we, from Sensec point of view, teamed up together with HP, Henriksson, Vinnova, Volvo, CGIT, and more, and created a lab simply to facilitate experimentation as quickly as possible, so we can learn together. Because we realize that on a fundamental level, it's the same challenges, and we can collaborate there. And then AI Sweden is the perfect platform. So what we've done, we set up an infrastructure here that is basically where you can build Legos. We have edge devices, we have core and cloud, that various applications, the open source, very free to download for yourself, but the proprietary frameworks are sometimes quite difficult to get your hands on, and that we try to facilitate already from the beginning. I also want to emphasize here that the setup we have is on purposely built to be as real as possible, or as close as possible to reality. So we can go all the way from simulation to almost identically to what we have actually out there implemented. And there is a good point of doing this, because a lot of the challenges when it comes to federated learning is about the practical part. How do we communicate between the edge node? How do we maintain security? How do we update models back and forth? Where should it be aggregated? How should it be aggregated? So there are lots of question marks. And to speed this up and to accelerate, we have set up this platform, which we call Edgelab. And I want to highlight that for all AI Sweden partners and project participants, the lab is available for you. And as Fredrik Bruhn mentioned, we're now also taking it in direction where it's compatible with space. It is already compatible in some extent, and that's why we have the collaboraton here later on. But we will adapt it over time. So if you want to engage and you want to use the facilities that we host here and the infrastructure, it's me, Ebba over here, and our project manager based in Malmö, Erik Wilson, who are your main contacts person. And you also see there the wizards. So since this is an exploratory area and it's a lab and it's a test environment, everyone working with the Edgelab, we call ourselves the wizards. Hence also my title of Proof of Concept Wizard, which I think is quite fun.
And we also welcome other wizards from partner organizations. If you actually want to spend time together with the other wizards, just shout out and we'll be happy to have you join the team. Yeah, for a short period of time, or longer, extended, it depends on what you want. But we definitely welcome that. Yeah, and that's a really good method for us to share knowledge, know-how. So you as an individual on the partner organization can come here 6 months, 1 year, be a part of what's happening here, joining other projects, developing your skills, and then bring that back home
to the company you're working for, or organization for that, or academia. And that's all from me. I wanted to keep it short so we keep on schedule here.
Short and sweet. Very good, Kim. Thank you so much. So we'll take a quick break, 5 minutes to fill up your coffee cups or stretch your legs. And then we'll see you back here at 9 o'clock for the next presentation. We'll leave the meeting open, so you can just mute if you're a panelist, but come back at 9 o'clock and we'll start again. So we're back again. We had some really interesting presentations just now, and we are continuing on that same topic. But first of all, we just wanted to show you this map of where we have participants from to this event. And I think it's pretty amazing actually how international it is. And just imagine also having all these satellites connecting us.
Yeah, and also to see that the interest is sort of universal around the globe. And I should say good evening to the ones joining us from Australia.
Exactly, and maybe very early good morning to some others.
Yes.
Or middle of the night perhaps. But now we're moving to Russia for a bit. So we have with us Evgenia Novikova from Smartilizer. Good morning.
Hello.
Hi.
Yes,
Hi.
hello. I'm glad to see all of you. Yes, so I'll open my presentation.
Yes, please. And we can hear you fine, so that's great.
So I can jump in between here and say that Smartilizer is one of the AI Sweden partners that are very, very active in Edgelab.
That's true. That's
and
really true.
they have interesting projects in the works and also demos. So for our collaboration attendees, take the opportunity later on during the collaboration to talk to Smartilizer, HPE, and Unibap and the other mentors that are available.
That's true. Yeah, exactly.
Yes. Please, Evgenia.
Yes. Okay. Hello. I'm really fascinated to present our results after very interesting reports. So today I'm going to present the results of our research devoted to the federated learning tools and frameworks that was performed by our team from Smartilizer and headed by our professor Van Hewlett. And yes, you have been already presented the concept of federated machine learning, so I will be very brief. So it is relatively novel computational paradigm for collaborated learning, and it emerged in response to the stricter requirements for personal data processing. And its key idea is to leave data on sources and perform training locally, and then transmit only models parameters in order to produce a global model. And certain benefits of this approach is that we do not need to transmit the large volumes of data, that we decrease the risk of unauthorized access. And of course, we do not need to integrate different data sources, different data formats. That also makes analyst life a little bit easier. So very briefly, the key features of a federated machine learning system. Depending on the computational resources of the clients, their availability during the training process, it is possible to outline cross-silo settings and cross-device settings. In the cross-silo settings, the typical examples and the typical clients are organization or data centers with extremely large computational resources with a high availability during the training process. And depending on how the machine learning processes are orchestrated, including how the aggregation of local model is performed, it is possible to outline centralized architecture and decentralized architecture or swarm architecture. And the last, but I think not the least, feature of the federated learning is how the data are partitioned across their clients. So if all clients share the similar set of attributes, but their information is about different objects, then we talk about horizontally partitioned data. But if the clients share information about the same objects, but different its attributes, then we talk about vertically partitioned data. So, and in our research, we tried to understand the current technological level of existing tools and frameworks. We were interested in knowing what types of data partition they support, what analysis models they support, and what is their overall performance. So here you may see a list of frameworks which were evaluated by us, it's quite long, I think. It includes TensorFlow, Federated, from Google, the Federated AI Technology Enabler from the VBank and PaddleFL framework from the Baidu, both are from Chinese. So the PySIP from Open Community, Open Mind. And this slide shows the key findings. So you may see that we have analyzed rather heterogeneous set of their characteristics, including not only specific features for federated learning, so the models, data partition, but also the contribution, how many contributors they do have, because this impacts actually on the rate of release of new versions and etc. I also need to tell that the major set of experiments, though we are continuing working in this field, was implemented in the winter-spring period of this year. That means that some frameworks have already released new versions, but till now, only few of them have released versions. For example, two of them are proprietary tools. This is a Clara SDK and IBM Federated Learning framework, but they are proprietary ones. And Clara Training SDK was initially designed for medical tasks. And only two open source frameworks have released versions. This is a Fate from the VBank and PaddleFM from the Baidu. And you also might see that actually they support variety of analysis models. They support two types of data partition. And what is even more important, they provide not only simulation mode for experimenting with federated learning, but also a real federated mode that could be deployed distributedly. So that is why our primary focus of our research was done on these two systems. Here you may see the experimental settings. So we use the Google virtual machines, and you might see the characteristics are quite high. And this is explained because the requirements of frameworks are also quite high to the resources. And as a test data set, we used real-world data set from the Smartilizer group. It describes movement of industrial vehicles. It is quite difficult data set for analysis, as it is not balanced, and it varies in volumes of data for different types of vehicles and different distributions of samples across the classes. So we also model different types of data partitions. So we implemented a set of series for horizontally partitioned data, for vertically partitioned data, and we evaluated their, we mainly evaluated the accuracy, the training time, the network traffic generated by the frameworks during the training. And so here you will see a set of slides first devoted to the horizontally partition data experiments, and then for vertically partitioned data. And what I must say that in terms of accuracy, the results was quite expected. We see that gradient boosting decision trees showed quite high results in accuracy, while logistical regression was not quite good. So its performance was not good. However, we actually received very surprising results for the temporal characteristics and network performance for differentially private stochastic gradient descent. This is DP's get there. So here you see that gradient boosting decision tree time is comparable to differentially private strategy, aggregating strategy. However, in decision gradient boosting strategy, the homomorphic encryption is used, and this is quite resource-consuming privacy-preserving technique. While differentially private is quite lightweight, should be quite lightweight technique, but in fact it resulted training time for a differentially private strategy turned to be more than 5.5 hours for 4 clients in different regions. That's, I think, quite long time, because this technique doesn't involve resource-consuming operations. Similar, we have similar results for traffic. So again, we have quite high values for this strategy. And currently, we explain these results by some internal implementation of this strategy in ParallelFL. We are still continuing analyzing and investigating this problem. So in terms of vertically partitioned data, this type of data partition is supported by ParallelFL and Fate, but both of these frameworks support different privacy-preserving encryption techniques to preserve privacy of input. In ParallelFL, developers use classical multi-party computational protocols, while in Fate, developers use homomorphic encryption, and this difference actually results in difference in overall performance, in training time and accuracy, and ParallelFL generally outperforms Fate in these parameters. However, Fate supports linear models for classifications and gradient boosting decision trees. Here, we have just a few slides that present the overall behavior, and we see that their performance depends on number of clients, size of the batch size. The similar for gradient boosting decision tree, the performance depends on number of trees, number of clients. However, developers introduce some novel algorithm to secure privacy of the data, iterative affine, that allows decrease slightly the time and of training, so increase a little bit temporal performance of these models. So, and here our summary for analysis of these two frameworks. We see that for Federated Security Aggregate, ParallelFL slightly outperforms Fate. However, Fate supports more analysis models, linear models, neural networks, decision trees. It supports even segmentation models for vertically partitioned data. That's why, in general, we would recommend using Fate. Its behavior is also more stable, more predictable when training, when performing analysis tasks. And currently, we continue our research and analysis of federated frameworks with particular focus on privacy. And we also developing a test bench as a web service for different federated learning frameworks to analyze their capabilities. This test bench actually is targeted for developers, data scientists, and data owners to understand, to choose what is the optimal framework for their task, what is the optimal settings. Now I have a very 2 minutes video that demonstrates its key features, and I will start it, and I already have 2 minutes to show you it, and I will be commenting it. So the key idea that you can set up different types of federation, assign tasks for different federation, and see the details of these analysis tasks. So when you create a federation, you can setup, its topology, its scale. You can choose aggregating server and clients. So here we created a federation consisting of 2 clients, and now we can assign tasks for this federation. Again, we need to define its name. We select analysis model and the corresponding algorithm. For each algorithm, it is possible to specify specific parameters. For example, here for neural network, we specify number of epochs, batch size, and optimizer, and we could now launch this analysis task. Here we currently, our test bench supports Fate, but we are going to extend the list of available frameworks. So this is a nice picture for information about the task, analysis task. This hyperlink, by pressing this hyperlink, it is possible to open the native dashboard of the Federated Learning framework. So for this case, this is a Fate board where we see a pipeline, the progress of analysis task, the detailed log. So this task takes 10 minutes approximately. So we skipped this performance, and now we see that the task has finished. We have its progress, its status. So it's done now. And now we can also have a possibility to review the parameters of our training, to understand its performance, to understand the accuracy, and all detail log is also available for us. So thank you for your attention. Try to be in timely manner. And if you have any questions, I will be glad to answer them. Maybe not now, but in chat and in Slack, I and my team is available. Thank you.
Thank you so much, Evgenia. Great presentation. And as you said, you guys from Smartilizer will be available for the collaborathon part. So if any of the participants want to ask questions here in the chat or reach out by Slack or in the live meeting that we will open later, that is also possible. And you will be available for all 3 days from and back. So that's quite amazing. Thank you so much.
Thank you for your attention.
And now we have our next speaker with us, Fuglesang, who is professor at the Royal Institute of Technology, KTH, in Sweden, also a space advisor at Saab and retired ESA astronaut. We're very happy to have you here on this event.
Well, thank you very much to invite me. And I was asked to talk about the difference between human and artificial intelligence in space, or biological and artificial, actually, by Tobias at the Swedish National Space Agency. Yeah, that's not so easy. You first have to kind of maybe try to define what you mean by intelligence, and sometimes you wonder if you even have some human intelligence up there when you do stupid things like losing tools in space and such things. But today, definitely the human intelligence is still very much bigger than any artificial intelligence available. And I think that would be for a long time to come, and humans are more versatile, and you can make broader decisions because you have much more experience. To have some kind of intelligence, I mean, I think you need to have sensors and you have to make decisions. If you take the International Space Station today, it's actually equipped with thousands of sensors to make sure you know the status of this situation, of this International Space Station, that everything is working properly. And most of the data just goes down to the Mission Control Center in Houston or in outside Moscow, and they get analyzed there. But some of the data, of course, they also get directly analyzed by the computers on the station. And if something quickly seems to go bad, then the system might take decisions like maybe close down some fans which are not working properly, or starting a fire alarm and things like that. So is that intelligence or not? probably not what we would really call an artificial intelligence. But it will come. And one of the questions which is often posed is this: well, what do we need to send humans in space? You can send robotics. Why robotics not instead of humans? Now, some of the robotics which we kind of have is certainly not artificial intelligence. For example, we do have a robotic arm on the International Space Station, which works very close with humans. When you're doing a spacewalk, you might often be on the end of the robotic arm and you get moved around, but the arm is completely controlled by humans from inside the space station, or actually could even be from the Mission Control Center in Houston. So that's not really, it's a robotic thing, but it's not the AI. Now, I don't think one should really put the question humans or robots. It's both, and they should help each other. At least if you had a vision that we go to space not only to gain knowledge, which how is maybe our solar system constructed, what minerals are there on an asteroid, or can we learn more about the moons of the Jupiter by sending probes there? Well, if you just want to do that, then it's cheaper and less risky for humans to send robotics. But if you had a vision that humans one day will be able to live in space, that it's good for humanity, that we can move outwards from the Earth. Earth is our kind of cradle. We will always live here. We will take care of it. But we can expand our living sphere. We can expand how well we can live. Resources on Earth is limited, but if we can bring in resources from asteroids, other planets, we can do so much more. In that case, it's a goal is actually to have humans being in space, and then of course you have to send humans. I do see a future where we want to really have AI, and that AI very much, I think, is combined with the machine learning, ML, when we, for example, will help humans move into space. For example, you need a habitat on the moon or Mars. Why not send robots, which is you have kind of told them, learn them that, okay, you're going to build a habitat for humans, and this is what is needed. But we don't really know very well how to utilize the soils which are there, or what's the best way. But if they're really smart enough system, they can start to build our maybe constructions, habitats for us, and they will learn themselves while they're building during the time. In particular, if is on Mars, where the communication is typically 20 minutes one way, and 40 minutes to kind of get an answer, it's not very efficient to kind of control them real time. So I think that's a kind of interesting future for where AI robots works for and with humans. But let me kind of get back to a little bit more basic things, things which I'm a bit involved in myself, which I would call kind of AI and space. You heard about, if you were here listening from the very beginning, Tobias mentioned the space data lab, and Saab, as was mentioned, which I'm working with, they have building or are developing a similar system, which is called
So we
yes.
Mute
Okay.
me. But I think just a few seconds, so please go ahead. You mentioned Saab.
Yes. And so what, did I get broken or what?
It cracked up, at least for us, so maybe we can assume other participants have the same problem. So
okay.
From Saab is working on something similar.
Well, let's jump into the important thing. And so Saab is building a similar system as the space data lab called MIMOS, where they combine data from space, but also from other sensors. So obviously security company, defense company. So it's kind of that are the prime customers you're looking at. So you may look include combined with radars from ground, looking for bad guys coming in and things like that. But they are also then bringing up photos from space, but then not so much Copernicus, the European things, but more private companies like Planet Lab, which has well over 100 small satellite with cameras in space, and also data from radios you can bring in from kind of also space radios, kind of taking signals from ships, from other emitters, and bring together and combine it to an understanding what's going on. And in particular, then you want to see when things are changing. Suddenly there is a ship somewhere which shouldn't be there, and it may not have this so-called AIS, automatic identification system. There's a signal every ship should send out. But if there are some smugglers or bad guys, they often turn it off. Well, if you then can quickly get this information from satellites that, oh, here's a ship not sending the kind of identification signal, there's something strange with it, then can inform decision makers, hey, take a look on this ship. So you need a fast decision-making process. So you want to combine this with ideally actually taking the decision on the satellite, and then you kind of send us the notification of down to ground. And that was also something similar to what Fredrik Bruhn was talking of, Unibap. So we're working on now to kind of move this system, which kind of notifies when there's an anomaly, as you call it, something new, is not maybe so good happening, to make that decision on the satellite itself. And it's not the only question and have a smart algorithm. It's actually also a question of making it energy efficient, because you don't have so much energy on the satellite as you can have on a big computer set here on Earth. And that's a project we have a little small project together at KTH and Saab and Unibap, actually doing that, and led by Professor Ingo Sanders at Embedded System KTH. So that is kind of what today is how you move AI, I would say, and to satellites. The other thing which has been mentioned, which I also think is very important for the future, is this how we get more and more satellites. I think Tobias mentioned 100,000, but at least will be tens of thousands of satellites within a decade, and to help them maybe not collide and things like that, if they can learn to take decisions themselves if need be. Swarm technology, so how they can work together. I think that is something which will be developed and will be needed in the future. And I'm actually part of a an application to WASP from KTH, where we are applying money to develop a robotic swarm technology for extreme environments or weightless environments, which is part of space, which I'm involved in, part of the underwater. And in the far future, I see perhaps an even bigger need for this swarm technology and robotic spacecrafts working together. And that's based on an idea I'm developing with some others, that if we cannot control the temperature rise on Earth by really decreasing the carbon dioxide emissions quickly enough, and the temperature seems to be not limited by even 2 about pre-industrial time, and approach 3 and more, well, can we then control the temperature some other ways? What about putting sunshades in space, which at least will not interfere with the atmosphere and things like that? And yes, it is possible. And you don't need to block off a lot of sunlight. It's a order 0.5% of the sunlight will decrease the temperature around 1 degree. And you would not put them in orbit around the Earth. That's not very efficient. You put them close to the Lagrange point between Sun and Earth. That is a point where the gravitational forces, together with the centrifugal force going around the Sun, balances out each other. And then, well, yeah, there's some other details. You need to go a little bit closer to the Sun because you have a force from the pressure of the Sun, actually. And you cannot put one huge shade up there of the order 1 million square kilometers, but you can have millions of shades of the order of maybe tens of square kilometers, something like that. And they have to be able to work together as a swarm, so they don't collide. And also you can optimize how do you do the shading on Earth to do that. So that's something where you definitely would need AI swarm technology for robotic spacecrafts in space. So, but bringing back the human dimension, again, I think the human intelligence will, for a very, very long time, hopefully forever, beat at least some aspects of the artificial intelligence. Of course, you can never, but AI can make quicker decisions on most things, but the versatility and the kind of wish to do things that we humans want to do, I think that's will be the human part of it, and hopefully forever. So yeah, I think I stopped there since I kind of promised to have a question and answer session. So how do you want to do that, Ebba?
Yes, now we're back with you. Kim is soon coming into the picture as well. Thank you so much, Krista. And we have the Q&A tab open. I've seen 2 questions come in already, but please use that function, attendees, and type in your questions, and we'll help Krista to see them and read them out loud. But first, Kim and I wanted to ask one question. So this Edgelab here at AI Sweden is focused on edge learning. So trying to train the AI model actually out on the edge devices. Is this something that you work with or have any experience of already, or how far away is it that we can go actually training up in space?
I'm not really working myself with it, but it is part of this vision to kind of get the efficient system on satellites, so that the satellites can take decisions. That's the first one. So you might start by training the system by data on ground, and then you could actually send it up, implement it on the satellite which is up there. But ideally, the next step would be to that they can learn why the system can learn while it's in space. That's clear. So that is part of this project which I mentioned on KTH and Saab, but I'm not the kind of scientist involved in it. I'm more the organizer involved in it.
But we look forward to hearing more about that going forward, because I think this will definitely, this is kind of the starting point of something that will take off in the Edgelab and with the connection with Swedish National Space Agency and the Data Lab, etc. So all these collaborations, I think, will just bring us up to speed. But so we have a question from Lucas Ambjörn, one of the Hyper Island students that are working with AI Sweden right now. And he is wondering, Krista, do you believe that humanity have enough determination to eventually colonize space?
Yes, I think we're kind of in the very start, first step to do that. And it's kind of depends on what you mean by colonizing space. Space is probably infinite, but if you say colonize our planetary system, by moving first and having some people living on the moon and later on Mars, and then going to asteroids and utilize that. I think we are really starting to do that. Partly we have had people living in space since, actually the first space station was in 1971, and since then most of the times people have been living in space, and the International Space Station have been permanently inhabited since 2000. But going further, it has been taking some time, but due to guys like Elon Musk, who has this vision and the capability to actually do things, really. I mean, he's building now his big Starship, super heavy spaceship combinations, which has the intention to go with send people to Mars with that. So I think we are starting.
So the determination is definitely there then.
Yes, not everybody, but enough people.
And building on that question, you already identified Elon Musk and SpaceX. In your opinion, what are the other key stakeholders to making this a reality coming forward?
Well, it will go faster if you have national space agencies which are supporting it. At least one has supported it. It's good if they can also have some help with seed money and things like that, which I think NASA has been very good at helping it. A little bit more, less interest in Europe to kind of support human space flight and exploration. It's been some, but not so much. And then the other companies, I mean, soon, Tina and Tom Sjögren, that kind of people who just have this vision and ideas and bring forward. So there's some many people, and entrepreneurs is one very important part of it, and dreamers is another one, but national space agencies also.
Thank you. And we do have another question from the audience, from Dean, and it kind of ties back to the first question that we have. And his question is, how does the space activities look like in 10 to 20 years, do you think? And how fast would that be growing? And how fast would you like it to be growing?
Space activities are growing very fast. And it's in many ways. I mean, partly because of miniaturization, so it's you can make more capable satellites which are much smaller than before. Parallel with that, rockets are being more efficient and cheaper to send things up to space. So those two work together and increase the number of satellites up there. And people are kind of come up with new ideas what you can do in space, what you can utilize data for. But most of what we do in space is for the benefit of Earth. And most of the satellites are kind of these mega constellations of communication satellites, where Starlink is the first one, and OneWeb now probably the second one with thousands of satellites. But then it's even starting to, definitely there's a lot of plans now, things being built to go to the moon. And this time it's not only the US, it's not only the kind of NASA, it's many private entities as well. So far, yeah, Elon Musk again, he's even planning to send people to moon, but they're private companies who have ideas how they can make money of kind of just building moon landers and things like that. And 20 years, I mean, within 5 years, probably we'll have the first people walking on the moon, not in 2024 is what was said, but 5 years from now, I guess. 10 to 15 years, I think we'll have people on Mars, and then we start to also being able to utilize, I think, resources from the asteroids. So we will kind of leave just the Earth's orbit area. We will start to go into deep space.
That's basically just around the corner.
Yeah.
After this pandemic is done, then we move to space. But so we have ESA coming in for a short presentation later, for example, so the European Space Agency. What do you see, how much international collaboration is needed to actually fast forward all of this?
I think the biggest drivers are private, actually, because government money can only do so much, that it can take the big risks in the beginning. But if you want to have a long-term activity, which is not only some basic research, it must be a possibility to earn money from it, or it might be something very visionary, which people are dreaming of. So the space agencies are important. They are really crucial for seeding things and taking the big risks in the beginning, but then we have to have the all the commercial actors and players. So and that's what I see is happening now. I mean, for a long time there was not much commercial money in space. It was mainly government money. I don't know if that was an answer to your question, actually. What was the question?
The collaboration required. So potentially then private actors could collaborate on these things, because we see a few of these different interests pop up, Elon Musk, obviously, but there are others as well. But do you think someone can solve the problem alone, or is collaboration actually needed?
Well, it seems Elon Musk can solve it alone, but I think it's beneficial with collaboration. The best is, I think, if you have some collaboration and some competition, because I mean, we all know that it goes faster and you're forced to work harder if there's a competition. So the collaboration was absolutely fantastic for the International Space Station. It's still, I mean, it's soon the only place where Russia and America is working together still. But doesn't work as fast. But since China started to come up, then America said, oh, we better go back to the moon now, and we probably start to go serious going towards Mars. But now it's not only the US government saying that, also it's US kind of private companies.
Interesting. Thank you so much. So we have one more question, and that will be the last question from the attendees. It's quite a long one. So we know that technology and satellites are here to stay, but how do we prevent the night sky from being ruined or polluted by the many satellites which will occupy space in the future, both from a cultural and astronomical perspectives?
Yeah, that's a challenge, not easily solved. I mean, it became a bit obvious when the first Starlink satellites were launched and astronomers started complaining. At least SpaceX then were very willing to work with the astronomers, and they were trying to find solutions to decrease the reflectivity of their satellites, and that has helped. I think that is the way to go. We try to kind of work with each other, but it will be a little bit of a kind of controversy between the benefit of having all these satellites and with the benefit of the, let's say, the human culture to be able to see the stars as we used to. On the other hand, more people are definitely already affected by that, because most people are living in towns, big cities these days. So you don't see many stars anyhow. But of course, you want to have the possibility.
Thank you so much. And I just have one more question. Do you think there's other life out there?
Oh, definitely.
Yeah.
I think all scientists are convinced that there are life in other places than on Earth. We don't really know how kind of life started. The very first step between most simple molecules to DNA and what kind of keeps life going. But that it only would have kind of happened, that step on Earth, that seems extremely unlikely. We know there's hundreds of billions of stars just in our galaxy, and we now know that most of the stars we can look at closely, they have many planets also, like we have around the Earth. So of course there must be planets which are similar conditions as we had on Earth, and why should not life have started there? So life definitely, but it might be simple lives. How many civilizations are there right now? That might be much tougher question to answer. Since universe might be infinite, but at least the observable universe has hundreds of billions of galaxies, you know, to the 100 billions of stars in our galaxy. It must actually be civilizations other places also, but
that what we call a cliffhanger. Ooh.
Actually see some other civilization. We don't even know how long a civilization will live, which is another kind of concern. They may extinguish themselves too fast.
Very interesting. Thank you so much, Christer. We really appreciate that you could take part in this event. Thank you for sharing your thoughts.
Thanks for having me.
You might be on for a little bit more. If anyone wants to type in another question, please feel free to do so. And Christer can answer by typing the answer. Now we'll have a quick coffee break for another just 2-3 minutes. And we will be back here at 9:50. So we'll keep the meeting open, be back at 9:50. Thank you so much.
I will actually sign off now, but hopefully join a little bit later through the other channel.
You're welcome. Thank you so much, Christer. Bye.
Thank you.
So welcome back again. That was a great talk with Christer Fuglesang, and he also segued us into the next part of this event. We have a pre-recorded presentation from Pythom Space, Tina and Tom Sjögren, really true adventurers that are building rockets in California. And that's what Christer mentioned, these private initiatives on people, making it easier to actually access space. So we will see this presentation, and at 4:30 to 5:30 tonight, we have an open after work session that you may be welcome to join if you have time. And that's the meeting link. So if you want to join that and you're an attendee now, reach out to our email addresses in the chat and ask for that link. But for now, we show you the presentation from Tina and Tom.
Hi, everybody.
Hi.
Thanks for having us at this event. You guys are working on some really cool stuff, and we are honored to be invited as part of that. Now, this is taped because we are in a different time zone. We are in California, but after the event, we will be available for live question and answers. If you want to stay with us and let's chat. So, as I said, you guys work on some cool events. Well, as for us, let me give you some background. Tom here went to Stockholm School of Economics, and I studied science at school. We met at 20 years old, we married, and then realized that we had no idea what we wanted to do with our lives. So we decided that we would travel the world and see if we could find out. Now that called for odd jobs to save money. So we dropped out of school, in Tom's case, only 6 months before his final exams. Now this was entirely my idea, and I think my mother-in-law will never forgive me, even after all these years, and I can't blame her.
Well, so we took off around the world, and 2 years later we returned home. And now we realized what we really wanted to do in life. We want to travel more. Now, this would take some serious money though, so we started business together. And soon enough, it became clear to us that getting rich fast would actually take much longer than we thought. But at least we spread our wings farther in our travels until we found ourselves doing some pretty wild stuff. We climbed big mountains in independent expeditions, Everest, sailed to South America on an old coastal cruiser, and skied all along the North and the South poles of our planet. We got Guinness World Records for moving faster than most, and the expeditions also turned us into engineers. We were sponsored by Henriksson, who used us for motivational stories, and they wanted live updates. Today, that's a no-brainer, but this was before social media and smartphones. If you wanted to communicate from places like Antarctica, you either had to bring a truckload of technology or come up with a better solution.
So, what better solutions did we come up with? Well, on Mount Everest, what we did was that we built lightweight stations, Wi-Fi stations, all the way to the summit for the first live dispatches from the mountain. Skiing to the South and North Poles turned out harder, more difficult. Why? Because now we would be on the move all the time. So we built a communications package that we could actually carry on our own bodies. And this package even fit in small Pelican cases. And when other explorers saw this, they wanted this for their travel. And this was the birth of our new startup, Human Edge Technology, that also took us to the United States. We named the package Contact for Carl Sagan and the movie, of which we were huge fans and still are today. We spent 8 years in New York City, developing software and hardware for lightweight missions, and we got some really cool customers, NGOs, the military, even NASA at one point. And then, after that, we moved west. First to Colorado for some skiing, and then in an old, really cool Airstream, we went to Silicon Valley. We were called there by the siren of the internet that was just budding. And it was such a wild place because there was a revolution going on. Google triumphed search. Zuckerberg took social media. Steve Jobs was the king of hardware.
And we stayed actually 5 years and immersed ourselves in smart manufacturing, big data, and advanced software writing. So this is also when we had our first encounter with artificial intelligence. We got an invite to our mailbox, and over at the Museum of Computer History, there was going to be a computer that would play Jeopardy against a bunch of pros. So we took our seats and we watched in awe Watson blow all the Jeopardy stars out of the water. But even more fascinating was watching the audience. At first, they all cheered for their own species, the humans on stage. But as the game proceeded, though, people started to increasingly get annoyed with the players, and they began siding with the robot.
Today, the United States military often wrestle with this dark side of our nature. We run with the winners, and we tend to trust authority, and we tend to trust authority a little bit too much. Recently, we actually attended a United States Security Artificial Intelligence conference, and they complained about agents at an airport. What happened was that this was at a luggage check, and if the computer said that the bag was a cat, the agent would actually hold the luggage, despite passengers pointing out it clearly was a bag. Back in those days, Silicon Valley was a vibrant and open place with meetups all around. We were invited to Google. We would eat at their cafeteria. We would take machine learning courses from Andrew Ng. We would experiment with generative adversarial networks, the GANs, and we would chat with a guy named Guido van Rossum about a fairly new programming language called Python. We learned smart machining at the tech shop Makerspaces, and we interviewed airspace engineers already back then about the viability of small rocket ships to space. As explorers, our inspirations came not from the large armadas colonizing planet Earth, but from the individuals and small teams who went first into the unknowns. The Leif Erikssons, the Nansen, the Cook, the Mallory, the Lewis and Clark. Our leading star was a Norwegian guy. His name was Roald Amundsen. After the huge Franklin expedition failed to cross the Northwest Passage, and not only that, they lost all the 150 men in the process. They all died. Amundsen broke through this passage. He did it in a fishing boat and with only 5 of his friends. So we asked ourselves, if the strategy of light and fast worked so well in our past, could it be applied to space travel? We asked ourselves. And that's where we are at right now.
In space, artificial intelligence is everywhere today. It's guiding satellite swarms, it's observing our planet, and it's adjusting the trajectories. But AI still only works in closed environments according to the present conditions. And if we go back to the military speak, the robot can go and stand in that corner, but it can't perform intent, such as don't be a target or win the war. As you all probably know, companies like DeepMind are training for this exactly. Mainly with joysticks in artificial environments. In other words, soldiers are playing games and the computer is watching, but that's not of practical use to us just yet. At the foot of Sierra Nevada, Python Space is a big black garage just off Main Street in Bishop, California. We are 7 people in the core team, supported by a fairly large global network, building rockets and landers for a complete space travel system. Using the same engines and propulsion system, our rocket ships will take us to orbit and straight to other rocks, moons and planets in the near solar system. We build everything from scratch, and we use all the tricks we learned during our lightweight treks around the world, and also from the engineering styles of Silicon Valley. We use straightforward machine learning every day, so let me just give you some very practical examples. We use computers to design everything these days, not just the rocket and engines, but also to build various test stands and even before changing interiors at our shop to prepare for new steps of manufacturing. Basically, we just do the math, we feed it into some design software, and the computer builds a 3D model. And before going to production, we test the expected parts performance using yet another set of algorithms.
Yeah, for example, on firing, our rocket engine reaches a temperature more than half the surface of the sun. So how do we prevent the engine from melting? Well, you know, I got one of them right here. One of our engines is made of incl, the exact same material that they used to land up on the moon, except this is 6 years later, so this one is actually 3D printed. It's so cool. It's double-walled, so that the propellant can go through it and cool it before it actually reaches the combustion chamber and combusts and give us our kick. For this to happen, inside this engine, there are 200 intricate channels. Back in the old days, you would have to build a number of these precision engines basically by hand. You would attach temperature sensors, you would test it from there. Now, this is, of course, a very complicated and time-consuming method. So these days, what we do is that we test the results using finite element analytics tools. Fluid dynamics, general mechanical analysis, vibrations, temperatures, all this can be tested in the computer before the engine actually meets the real world. Now, these are tools such as Console, OpenFOAM, or Autodesk CFD, Computer Fluid Dynamics, that break our engines into millions of tiny parts that we can use to predict engine behavior in various physical environments.
And if you look at the engine level, imagine if you try to understand just from the top of your head how flow of, say for instance, 30 liters per second of propellant is cooled, then superheated, and shortly after transformed from liquids to gases, and in our 9 engines simultaneously. Well, traditional equations will give you basic understanding, but computational fluid dynamics software visualizes the process so we can actually understand it. At the full rocket ship level, building the full rocket, the software turns much of the sheet metal into little plates, shells, and computes how they break and or fold during different conditions and stresses, how they will vibrate, how heat moves across different parts, and many other physical features. The more of these individual elements, the better the result. Big enough computers and machine learning allow millions of them, and we can reduce computational time significantly to optimize analysis results. The partial differential equations Tina talked about, Navier-Stokes, that we use offers about 50% reliability. This is still a huge help when trying to understand complex nonlinear flows, especially with high Reynolds number, lots of turbulence, but it's not really good enough.
Yeah. So, but you know what? Even with 50%, it's still helpful. But I gotta tell you that deep learning techniques could increase this a lot while lowering the data usage, and that would be a game changer. A true digital twin for our actual rocket would basically cut out all the testing. And now we could go just straight to automated manufacturing. This kind of artificial intelligence can't entirely replace the use of experimental methods at Python, but rather the two complement each other. We can test general assumptions that we have, but we are not yet at the point where we actually can just take the predictions at the face value and assume that they are correct. Remember the agent with the cat in the bag, right? But once we get a general feeling that we're on the right track, that the part will perform as we hope for it, as we intend for it to, we send the design software to a computer-guided manufacturing machine of choice. For example, a 3D printer. Now, let's say though that we are not entirely happy with the design. For example, the part does what we ask it to do, but it's just too heavy. Now we can actually go back to the computer and ask for help. Autodesk has a generative design tool, and this is a creative algorithm. We input the loads, we input the constraints, we input the original designs. The software offers us alternative designs that meet those requirements. The shapes that you may not have thought of yourself. So where is this going? Well, let's just say that generative design is not regularly used in rockets just yet, but it should, and it will.
But once we're happy, the design goes to manufacturing. We have a CNC machine park and use high quality 3D printers to make our engines out of metal. CNC machining has been around for decades, but applications were limited before the advent of AI, making the process faster and more precise today. Some even say that manufacturing industry, in fact, is ultimately the main driving force behind AI advances. So computer-controlled mill, lathe, printer, and other allows us to produce with very high precision right here in this shop. This makes a huge difference in cost and delivery times compared to the quotes we get from the industry. Last Christmas, we actually made a single set of flanges in-house here, and we saved weeks, and the cost saving ultimately paid for the entire machine to make them.
Is there 20K or something?
Yeah.
Yeah.
There is, when you work with the CAD and you work with the CNC machines, there are no human errors. Prototypes will look exactly as they looked in the CAD file. So CNC machines are used for just about everything rocket related, from mechanical parts to electronics, miniature circuit boards, to guiding systems and trajectories. Trajectory planning is another nonlinear optimization problem, and we use an NLP solver, nonlinear programming, developed by ESA for this. These trajectory plans are, though, quite hard to handle, and the results are not exact, but neither are people. So, you take what you get. Rockets used to have manual flight termination systems, but that has changed super fast. Most flight termination systems today are autonomous, and manual systems, believe it or not, will actually be outlawed in the United States by 2025, in a couple of years.
Launching a rocket to space, to a specific orbit, means that you have to aim to hit the point that moves at 20,000 kilometers per hour. Now, many variables are at play as you're doing this. Winds, for instance. Winds are important. A wind speed that changes from 7 meters per second to 5 meters per second can actually throw you entirely off, and you're going to miss the target. This, again, makes for a huge lot of computer simulations and machine learning. Also, when applying for a launch permit with FAA, the Federal Aviation Agency here in the United States, we must submit predictions of what will happen if our rocket blows up at any stage. So, what kind of building will be in our flight path? How much is their estimated value? This is important for insurance. And where exactly will all the shrapnels fall? This is unreal, but that's what they want. And we're talking shrapnels here down to 1 decimeter in size. Again, lots of machine learning at play here. So artificial intelligence, what you guys are doing, is very useful for us already today. And we'd like to give you our wish list for the future, and not the far away future, for the near future. The most useful for us would be fast and easy to use live optimization software. That would be so cool. We will also really need AI to estimate entropy in combustion chambers. Again, hugely invaluable this will be, because today all of this is actually tested empirically.
Going to Mars, our biggest AI challenge will be Jonathan. That's something we are building here in-house. It's a HAL-like human-robot collaboration software. This set of algorithms will make use of all machine learning techniques combined. We talk natural language processing to talk to us, supervised learning to keep tab on the state of the ship, the sensors, and our personal health, and unsupervised learning with some sort of reward reinforcement system to predict spaceship maintenance, ride the galactic highways, and score downloaded internet, because we need to do that to bring it with us, for solutions to questions presented by us.
Our goal with artificial intelligence is not to build something that's smarter than us, but to actually improve our own reasoning, much like the machines already enhance our machine shops so much today. After that, who knows where the ships will take us, right?
Thank you.
Thank you.
So that was the presentation from Tom and Tina Sjögren from Pythom Space. So a Swedish company, but they're based in California. And as I mentioned, they will be here this afternoon from 5 o'clock, but we'll start the after work session from 4:30. So shoot us an email if you would be interested in listening into that session. Otherwise, it's open mostly for the collaboraton partners, attendees. But also, please shout out if you want to join us then. So now we have our next speakers from the European Space Agency, and we have Pierre-Philippe Mathieu with us, and also Massimiliano Pastena.
Welcome.
Good morning, Ebba. Can you hear me?
Yes, perfectly. Well, I was sorry with the link. So your name is actually not your name. You are Pierre-Philippe. And then we had Massimiliano with us as well. Let's see if you can come back on the screen.
Yeah, I'm here.
There we go.
Thank you. Morning.
We love to create confusion at ESA.
Exactly.
And
Perfect.
yeah?
So go ahead, please. You have a few words to say about ESA. And
Yes. So first of all, thank you very much for your invitation to this very exciting event. I think it's very timely. The reason is that in the field of Earth observation from space, which is looking at our planet with a variety of satellites, some of them operational for environmental monitoring, some for meteorology, and some for research. All these data becomes extremely big. We talk about 10 plus petabyte per year, extremely diverse, very different techniques, sampling, error, etc. So we need machine learning to actually make sense of this data and to find the information in it, to fuse it together in order to get the most comprehensive picture, and also to improve the prediction of what the state of the planet will be. So AI, and in particular machine learning, has been hitting our field since a few years now, a bit of a delay compared to other fields, but it's really changing the way we do things. It makes it automatic, scalable, but of course we critically need domain experts to interpret this, because remember that it's only statistics. So this is what's happening in the PhilApp. We are trying to develop some use case with this technology to understand the strengths, the weaknesses, but also to bring it at the edge, because there are a lot of exciting stuff happening at the edge. If we have the ability to run machine learning on very small chip that are in the satellite, suddenly the satellite can become smarter. It's like if you have the brain coming closer to the eyes, and so you become more reactive. And we are exploring this field. We call it tiny machine learning. And we have done a demonstration with a mission called FISAT, and Max will tell you everything about the family of FISAT we are developing. And my message to you is that we need, what we really need today is talents, AI experts. We need enthusiastic entrepreneur people to come and connect with us. We have opportunity in the PhilApp to have visiting researchers, so you can connect with me to explore this further. And we need these brains to work on these very important problems of how to use this big data to better manage our planet, because at the end of the day, AI is just a tool, and what we want is better understanding and better stewardship of our planet. And I'll stop there and leave the floor to Max. Many thanks.
Hello, good morning. Can you hear me and see me? I think so. So good morning, everyone. Okay, my name is Max, and I'm today talking about our FISAT. So let's start first from the name. So most of you have recognized phi as a Greek letter. Someone smarter, I think, among you will recognize the golden ratio. But what is a phi really for ESA is something really special. No, Pierre-Philippe mentioned the phi lab. Phi for us means innovation, means future, means thinking out of the box. Once people throw heart over the obstacles, what we really want to do is to throw our brain over the obstacle and win and increase and help people, the scientists, to better learn and improve and increase the knowledge of our planet Earth and more in general of our entire world. So what is so special about FISAT that to deserve this name? So FISATs are satellites to demonstrate in flight the enabling capability of disruptive technology. And the first two FISATs has been devoted to demonstrate the enabling capability of artificial intelligence in orbit on the edge, as Pierre-Philippe said. What we really are doing is try to demonstrate what artificial intelligence can do. Of course, we like to think that all our satellites are intelligent. We don't think that any of our satellites is dumb or stupid. But what we really want to do is to implant the brain into the satellite in order to do new acquisition, to improve the measure that we do of our planet Earth. We want to give to the science better data, more data with higher scientific content, higher level of information, and so on. So to help them to improve the knowledge of our planet. But what, for example, we have done with the FISAT-1 that has been launched last year, we have insert an experiment in one of our mission for cloud detection. I know that most of you are thinking what is so exciting in cloud, in detect the cloud on image of the Earth. And what is, I mean, do you really need artificial intelligence? And what is so smart to detect a white pixel? But it's not really like that. It's much more exciting than what you can think, because the really enabling capability is to do it accurately and reliably. So imagine that you have a satellite to monitor, for example, the ice content of the polar region. Everyone knows how much is important the ice content on the polar region for our climate and the climate of the overall world. So imagine that you have this satellite that go over the planet of the poles and download the image. Most of them will be covered by clouds. And the satellite will spend a lot of time downloading basically useless data. So what we are trying to do is to make everything much more efficient, enabling the satellite to acquire much more image, get rid of the cloud coverage, and give to the scientists, download to Earth to the scientists only the part of the image that is interesting for them, meaning the part related with the ice content and the ice edge. So what happens if the algorithm to detect the cloud misinterpreting snow by cloud? It's very simple. It's very simple to do that. It's a very high challenge to distinguish between snow and cloud. You are going to basically to lose forever interesting data. Maybe you cannot retrieve the age of the ice, and you cannot understand how the eye is moving, is retracting or expanding. I mean, mostly retracting, unfortunately for us. So the key thing is to do it reliably and accurately. And this is what basically the first FISAT has demonstrated. It's been the first deep convolutional neural network flying on a satellite, detecting clouds over hyperspectral image. And what has been demonstrated is that we can reliably remove cloud, increasing up to the 70% the scientific content of our downloaded data. And this was a huge success, so successful that we thought about pass to the FISAT-2, the second satellite of the series of the FISAT. This time, what we wanted to do basically is to give the possibility to everyone to access to the intelligence on the edge of our satellite. In fact, what we are building and will be launched next year will be really a flying laboratory, which will embark basically a platform which will be able to upload apps for Earth observation. Basically, when it will fly, it will be so as simple as you download the app on your smartphone, to upload to our satellite your app to retrieve information from our images. And these will be open to third party that can develop app and upload and monitor. And with this, I think that I will stop here because time is constrained. And thank you very much for hearing me.
Thank you very much, Max. And I would like to point out that ESA here is both a technology driver and a funding agency, quite similar to how the National Swedish Space Agency is also a funding agency. And this ties together this event because here we have partners of technology driving side that you can team up with, you can get funding, and you can utilize our resources to do your development and exploring. And on the topic of resources and Edgelab, one of the funding partners.
We have to wait. We need to say thank you to, to Max and Pierre Philippe. And please, before you guys leave, can you just share your contact details, if you don't mind, in the chat, and maybe a link to the FISAT-2 project that is coming up? That would be really valuable. Then people can get in touch with you.
Thank you very much. I will do for sure.
That sounds great. Thank you so much for attending. We really appreciate it.
Yeah, and thanks for taking your time.
Thanks.
Now we have our next speaker from one of the founding partners of the Edgelab.
Yes, HB. Welcome, Sorin.
Hi guys. Hello everybody. Happy to be here. And I'm going to quickly start, and let me see if I can share a couple of slides just to make this a bit more fun and to play a bit with images. So it worked yesterday, but it should work today as well. So, okay, let me see if you can actually hear my desktop, see my desktop right now.
Not currently, probably in a second. Okay.
So give me a second.
That looks great.
Okay, so which screen are you actually seeing? Redefining edge?
Yes.
Okay, great. All right. Okay, good. So what a list of speakers, right? So I don't normally get intimidated, but after listening to a bit of the agenda that you guys put together, you know, I'm thinking that I need to wrap this up. So let's try to make this as painless as possible for everybody, but also to have a bit of fun. Right. So basically, I'm going to talk about this idea of redefining the edge. and how in time we're actually looking at thinking about the edge and AI at the edge and so on and so forth, right? Because at the end, we all know that AI, actually artificial intelligence, actually unshackled the constraints of IoT, right? We've been talking about the burst of IoT and all the data that was generating at the edge, but we were not doing anything with it. We're actually adding burdens on processes and so on and so forth. So now, basically, what we are doing is we are looking at using AI to unshackle all the constraints and to actually do and run analytics and make decisions at the edge. But let me quickly walk through a couple of points. I think you are all we have in the core a lot of AI. From what I heard, about a lot of artificial intelligence data engineers, data scientists, ML engineers, and so on. So I'm not going to spend too much time on this slide. But basically, I wanted to make just one very important point for me, at least for us, for HPE. So we all recognize that data is generating at the edge, right? And this actually can be smart hospitals, manufacturing, factories, power generating mills, and so on and so forth, as the Pythom team actually mentioned earlier. So basically, the data is generating at the edge, and then the data starts a very interesting travel, right? It moves somewhere to the near edge where data is being generated, where data is being aggregated. Then it moves back in the data. It moves in the data center where data becomes models, and then the models are actually going back at the edge. So basically, we are seeing somehow of a closed loop when data starts at the edge and then goes back at the edge under the form of models to be transformed in predictions, inference, real-time analytics, or what have you. So suddenly, we realize the importance of actually having the edge, right? Or understanding how the edge works and putting a lot more focus on where do we want to go at the edge. So my team initially started, we started a lot of projects around AI with edges, right? So we started obviously with sensors in manufacturing, and I think again the Pythom team and also the ISA were actually talking about the importance of understanding what the sensors are going to do, what will happen to them on manufacturing lines. All right. So the first place where we are actually using AI and we are advancing AI, as mentioned also before, is manufacturing at the edge. Then what we've done, we also looked at what happens if you're actually putting sensors in something that moves at 300 kilometers per hour, and then you still need to run analytics. So we've done a lot of very cool projects with Formula One teams, understanding how quickly we can actually make decisions when real time, well, it's real time. So we actually have 300 kilometers per hour moving sensors or edges. Then we actually took this a step further, and then we tried to tackle what we believed at the time is the ultimate edge device, us, or the ultimate sensor, sorry, edge device, us, meaning humans. So basically now you have AI, and we are running AI in everything. We are running AI on your tablets, on your phones, on your watches, and so on and so forth. Soon, your watch is going to tell you when you're supposed to eat, what your diet is going to look like, you know, how much sugar you actually have in your blood, and so on and so forth. So slow-moving walking sensor, sorry, edges, which is us. Then we've taken this one step forward, right? And then we looked at autonomous moving sensors and edges, right? And this is most likely down here on Earth is the ultimate, in some cases, AI problem to solve. Autonomous, connected, shared, and electrified driving, where basically we want to go from point A to point B, just jump in a car, read your magazine, sleep, do a piece of work, chat, while you're actually getting there. And all of that simply without actually moving one finger. So we are tackling all of those edge data and edge sensors, and we're actually thinking, what is the next step? Can we actually take this one step further? Well, we need to redefine the way we think about the edge, because why not? Space is the final frontier, or maybe the final edge. So then, some years back, we're actually challenged by NASA to see, can we actually put simple COTS servers that you can actually find to buy yourselves on the International Space Station, and we can actually run compute. But why would someone want to put, why would someone want to put actually servers on the ISS? Well, simply because we want to solve a very complicated but simple, or very complicated in space, but very simple problem here on Earth. which is bandwidth issues. So if you're thinking about the AISS, basically AISS communicates with Earth in a window, in a very small 2-hour window every 2 weeks. Basically and the window is about 2 gigabit per second every 2 weeks. And you only have 2 hours. So basically this is equivalent with about 1.5 meg per hour, which is, if you calculate in the bit, 100 times slower than your basic broadband in a window, but also it's about 10 times slower than the bandwidth you're actually using when you're listening to an MP3 on your iPhone. So it's really, really slow. So then what we decided to do, why don't we try to solve the problem by putting computers in space? In order to make sure that instead of actually pushing data or streams of data down to Earth, we're actually pushing information. We're actually pushing predictions. We're actually pushing the information that we actually want down to Earth to make decisions. So this is why we decided to go with 2 drawers, 2 lockers, and basically those 2 lockers are actually part of the Columbus module, which is basically the research lab on ISS, and it actually contains 2 lockers, and each locker actually contains 2 servers. And yes, they are proven in space and available on Earth. We actually have an EL4000, which is your ultimate HP edge device that actually contains an NVIDIA GPU. And then basically we have a traditional dual socket server, a DL360, that is actually looking at, apologies, that is actually looking at simply registering and why not zipping and actually sending data down to Earth. While the EL4000 is actually looking at AI/ML operations or AI/ML analytics. Now, the other thing is, why would I actually need the computing space? How do we actually do it today before we actually send this thing into space? Well, the way we actually currently interact with data in space is that within the window that I have explained, you're trying to pull archives down. Yes, gzip, a bit of different type of gzip, but this is what you're actually doing. You're pulling data out of space on a very small channel. So basically, what happens is that we try to think, what happens if we put a bit of compute? And instead of actually Mr. Jones saying, I want this data, putting it on Earth, running a small algorithm, and then pushing back in some more data in order to actually trigger more data download, why don't we actually put some computing space that is actually able to run the analytics? And Mr. Jones, or Mr. John Doe, is actually able just to pull in the final result. And while we're there, why don't we actually foresee and try to understand if we can actually bring burst capabilities into the ISS? Yes, burst into the cloud, which, if you think about it, they are not so closer than the ISS than Earth is. So basically, the charter of the spaceborne computer number 2 is onboard genomic analytics. Yes, this is the small AI/ML task that I was saying. Also then to actually analyze sensor data like LiDAR, visual, LiDAR, radar, and signal processing, but also to understand if we could, if needed, burst into the cloud. First, just let's say send the hello world into Azure, and then later on, why shouldn't we actually run the genomics jobs into the Azure as well? And finally, demonstrate that actually service high reliability and HA actually works in space as well without us intervening or touching anything at all. So this is why you actually have 2 lockers. So this is the initial task. And what we actually realized was that actually it works. So basically, one of the first tasks was to understand if cloud enabled works. So what we actually did, one of the first tests is to send the omnious and the ever-present hello world test. So basically, what we've done from the spaceborne computer in space, we actually send everything down to the command and control that actually basically then runs quickly everything without into the Azure, and then from Azure goes actually back to command and control, and then command and control actually sends everything to the spaceborne computer, just the data, which actually works. Yes, I know we still have somebody in the middle, but this is what we are working on, to remove the middleman in the future. Now, because I don't want to take a lot of your time, I want to actually think about what is coming next. So let's get a little, let's get back to Earth for a moment, right? So down here on Earth, what we are currently working on is not only to make cars autonomous, but also to try to understand how to actually bring them together. So this is why HP created something that we actually call swarm learning, which basically relies somehow very far away on swarm intelligence, but is a form of federated learning, just a bit, just updating that a bit with a couple of features. Couple of more features, but basically what is happening is that instead of actually running and allowing the car to go out, gathering all the data and running analytics on the car in itself, what we want to do is to bring all of those cars into one network and for them not to share data but insights. So actually, instead of actually sharing the data to train better and better models, we would like to enable a car in Mumbai in India and the car, let's say in Göteborg, for example, to be able to share whatever they see in the streets, but without sharing data, thus not breaking GDPR rules, data privacy, data security, and simply not breaking the laws of physics, because in some cases that is actually impossible. Data is governed by the laws of physics, laws of economics, and obviously the laws of the land. So we wanted to create a technology that allows us to share the insights, such actually bettering the prediction and the analytics that we can actually run where the edge devices are. So we are currently working with a lot of our partners to actually prove this out. Now, this is here on Earth. We just launched the spaceborne computer number 2 up there in space. So how do we bridge the gap? Because we do want to understand what is coming next into space. Yes, we've run spaceborne computer. Yes, it's running analytics right there. Yes, it is actually able to burst soon into the cloud as well. But what happens if we launch more? So this is where we are trying to challenge the art of the possible. And this is why Prasad Shastri is going to be later from my team is going to be later on participating to the brainstorming session. And also in the next couple of days is trying to understand the art of the possible with swarm learning. Why can't we actually think about, instead of connecting autonomous vehicles, connecting spaceborne computers that are actually able to be around the Earth. And in 1 second, instead of actually taking and sending information down to Earth, which is that common central location when everything might become a bottleneck, sharing the insights in order to make decision in a split second, right? In order to understand which sandstorm is actually going on to Mars, what should we actually react to, and so on and so forth. Why shouldn't we actually do this with something like swarm learning? Or any type of learning for that matter, but actually to create a network. Yes, it sounds like a science fiction movie, but why don't we actually create a network of spaceborne computers? In the words of Douglas Adams from the famous book, you know, everybody knows the Hitchhiker movie as well, Hitchhiker Guide from the Galaxy, space is big. So this is not actually going to be easy. So it is not like in autonomous driving when you're actually moving from A to B or going to your shop. Space is actually, or distance is peanuts in space. So basically, this is going to be a challenging problem. And this is why we have all the various scientists coming together, scientists like yourselves, partners like HPE, or partners like AI.SE. Thank you for your time and have a great, have a lot of fun in the brainstorming session in the next couple of days. Ebba?
Thank you so much, Sorin. We really look forward to having you on the brainstorming session as well. And thanks to HPE overall for all the work you've done so far in the Edgelab. I'm really excited to have you on board on this SPOC event.
Yes, and soon we will move over to starting the collaboration part of this event. There is a new link for the collaboration. It should be in your emails. It's also available on Slack.
And it's for a Zoom meeting.
Yes. That meeting will be open during the entire collaboration event. So you can drop in and have a chat with people that are on site and between yourself as well. I also want to highlight that on site, we also have data available from satellites from the European Space Agency, Swedish Space Agency, and the Space Data Lab of Earth observation. So that's good to have in mind.
And thank you. Now we have Tobias with us again, and you are the one who have helped us to get that data from the National Space Agency, and you will also, of course, be part of the brainstorming session. So from all of us, AI Sweden and the National Space Agency, Space Data Lab and RISE, we say thank you to all the speakers and also to all the participants. And we look forward to seeing you on Thursday at 3, where we can see the results from this SPOC. And what's really interesting is what's going to happen after that. How can we continue work together and work on these very interesting things on Space Edge? Yeah. So thank you for now. We will open up the meeting link at 10:45 for the brainstorming session. Thank you so much.
Thank you.
Yes, and thank you, Ebba and Kim. Really nice work done here. Thanks.
Yeah, thanks, Ebba and Kim. Congrats for the event. See everybody soon.
Thank you.